Okay, before I get started, just some logistics. I'm not going to give a lecture tomorrow, but I will be on Zoom for both of the class times to answer any questions. There, there will be one final computer assignment. It's going to be applying this output stuff that we've been doing, and also in the process, you're going to have to implement a couple of random variables that you've already found the algorithm for. And then the last thing is the final next Tuesday at 8 a.m. For those online, it'll be the same thing that we did. For those in person, it'll be the same as we did in the midterm, except it'll be 2 hours. It'll be the coverage will be comprehensive in terms of covering everything that we've done so far. You can have your 8.5 by 11 sheet, a calculator if you, or your phone calculator. I mean, back when our teacher said, "Oh, you're not always going to have a calculator in your pocket." Guess what, Mrs. Jones? Take that. Okay. And any questions about that, you can talk to me. But we're heading to the final lap here. I don't know if I even have it. Oh, and just for the Python folk, I've been having a little bit of difficulty with my Python. I finally have it straightened out, so I'm a little bit behind in terms of posting the Python versions of what I've been doing, but that all will be corrected soon. So just so you know. Okay, so here. Okay, we've been talking about output analysis, and what's important for that is because that's really the reason why all of this is being done in the first place, to answer some question and to answer it in a way which is statistically legitimate, meaning that if you're going to come out as part of the analysis, if you're going to say, for example, the expected value of this measure is so-and-so, that, or the value of this measure is so-and-so, then that you're clear about, well, first of all, was that measure obtained from a model that correctly, or at least accurately captured the essence of what was going on in the real system. But more than that, have you done the analysis in such a way that you're not just running it once, you're all beyond that, and you're not just running it multiple times and computing a mean, you're also including a confidence interval, which shows how, is a rough measure of how quote accurate that measure is. I mean, I put accurate in air quotes because that's, basically how confident are you that value is in fact, that your true value is in fact within that range. Okay, so now, so what does that leave? So what we've done is we've also identified that there are kind of two areas of the simulation that are of interest. One is the initial period, the initial transient period, and we analyze that in a fairly straightforward way by just kind of running the model for until some ending condition is met, doing that multiple independent times, and then forming the confidence interval that way. The challenge with that is that what it is that average that we're computing is the average of observations that are not independent or identically distributed. But by doing the independent replications, we come up with a so-called random sample, that is ID, independent, identically distributed values, and then we can then apply all that wonderful statistics stuff that you all know and love, which is that we can wave our hands at the central limit theorem, and then apply that formula for the half-width using the t-distribution. I mean, all of that is necessary. So what's the, so what else is there? Well, so as you may have, I mean, one of the things that that happens with this stuff is that, in a sense, there are almost never any definitive answers. They're just answers that create more questions. And so the problem which we kind of noticed last time, for at least some of our in that one model, is that the confidence interval may be too large for practical use. In other words, we may be doing everything correct statistically and from a simulation point of view, and the answer that we're giving, or at least the numerical part of the of what the decision is, has a confidence interval that's just sort of too big to be of practical use. One way to kind of think of that is that if our measure, if we're looking at, say, a combat situation, and we're kind of pre-analyzing a potential operation, and our primary measure that we're interested, the decision maker is interested in, wants to know what is the probability that this is going to be successful. So if we can create at least a reasonable model for that and run it, we can, you kind of run it and you get a yes or a no at the end. Did we win or did we lose? And you do that many, many times and you'll get an estimate of that probability. Okay, so we do everything correctly, and then you say, well, the expected value is, the expected probability is like 0.7 plus or minus 0.3. So that's, we did everything correctly, but that's not of any practical use, because you don't know if, in theory, it could be less than 50-50. So, and we saw that with that delay in the queue thing, where I think the half-width size was like 8 or something. So that's fairly large compared with the value that we had. So, and then we also saw in the Renegg model, it wasn't so much of an issue, just kind of doing things normally. We had nice tight confidence intervals that worked out well. So beforehand, you don't know if it worked out well or not so well. In highly variable simulations, what tends to happen is you tend to get big confidence intervals because of the variability of the system. And actually, if you sort of think about it, in sort of the naked queue, as it were, without any other things going on, the properties of the multiple server queue without any constraints on it can be kind of wacky. Whereas the presence of the renegging actually kind of calms the system down. In other words, the fact that customers are leaving is kind of a built-in adjustment of the queue sizes, at the cost of losing customers. But it's like, what happens is the actual arrival rate to the server is kind of almost automatically decreased due to the customers kind of leaving. Whereas if everybody kind of went in, then the queues might blow up, for all we know. Okay, so what's the difficulty? The difficulty is that when we do one of these experiments, again, we choose a confidence level, alpha, we've been using 0.05. There's no, 0.05, 0.01 are the two that you don't have to argue about. Does that mean they're right? No, but we choose our confidence. This is how confident we want to be. And then we choose our sample size. And then we're stuck with whatever size our confidence interval is. Because once we choose those two, we have no control over the size of the confidence interval. So what do we want to keep? I mean, so basically it's like we gotta ditch one of these if we're gonna do something different. Because as long as we're stuck with a fixed sample size, we're stuck. So what can we do? Well, we can decrease our confidence and keep the sample size the same. But, so it's like, all right, here's a 25% confidence interval. It's nice and tight. So, well, how confident are you really? Well, yeah. Okay, so we're going to keep alpha, and so that only leaves, that's the Sherlock Holmes principle. If you've eliminated all other possibilities except for one, then it's got to be that one. So we got to ditch the fixed sample size, and there are some issues with that. So this fixed sample size must go. So what does that leave? That leaves something called the sequential method. And this is a really interesting one, at least partly for some of us math geeks, that the mathematics involved are quite involved. It takes about, my recollection is the paper that kind of proved the validity of this took about 10 pages of math. So we're not going to do that. But it's nice and intuitive. So instead of selecting a sample size, I'm going to select a desired size of the half width. I'll call it beta, just Y, because, well, as you might have noticed, that the more Greek letters that you use when you're presenting something, the cooler it is. So, okay. And what I like about this is it's actually very intuitive, and this is one of the things that you can do in simulation much more easily than in the kinds of things that statisticians are used to. It was actually invented by a statistician named Wald back in the 1940s, before computer simulation was something you could do it with, and it kind of gathered some dust for a while until actually simulators rediscovered this and said, okay, this is pretty cool because we can do that. See, now, some of you are going to be doing in your thesis, many MOVE students do human factors thesis, where, okay, so what are your experiments on that? Well, you get somebody, let's say you're testing out some VR versus AR versus something else. So you bring somebody in, you set them up, you kind of do your thing. That's one. So the idea of kind of doing a sequential thing in that setting is actually not a reasonable thing. Why? Because your sample sizes are going to be very, very small if you're using actual people. And even in sort of bigger studies where they, like a psychology study where they learn a lot about the undergraduates that they kind of bring in, but still the sample sizes on that are relatively small. This is something where simulations can do. So the idea is, and it's kind of an extension of what we were doing in an ad hoc way the other day. That is, okay, the half width is too big. What do? You take more replications. So we did more replications. It reduced the size of the half width. And so the question is, okay, is that really a formal procedure? And the answer is no. It's just an ad hoc one. So here we actually formalize it. And what's nice is that you can kind of show that this is actually legitimate. So, and what do we do? We do just what you would think. We just keep replicating until our half width meets this criterion. We say we want our half width to be no more than thus and such. And then we just kind of run the bejesus out of it until that. Okay, so now what there's always a catch. So what's the catch? There are basically two catches. The first is that well, actually not so much the run length, the replications. I misspoke there. So the number of replications may be excessive, and we'll see a little bit of that in one of the examples that I'm going to give. And the other is that convergence is very slow. In other words, theoretically, again, under mild, all the usual assumptions, you can prove that this will actually, end. Like whenever you have an open-ended procedure, the question comes up, is it going to end? And can you prove it's going to end? And in this case, we can. Why? Because of, under the normal assumptions, our half width is the estimate of the standard deviation over root n times our t quantile. And as the sample size, as n goes to infinity, as n gets bigger and bigger, then what happens is, because these are independent observations, our standard deviation estimate is actually, so the term is consistent, meaning this is going to actually converge to the no kidding underlying standard deviation, whatever that is. We don't know what that is, but that's just a number. And similarly, the t distribution as the number of degrees of freedom increases, it converges to a standard normal, that doesn't depend on n. So these guys do not depend on n. But here's n. So how fast is the half width shrinking? As 1 over the square root of n. And if you're familiar with kind of how things converge, that's about as slow as it gets. Okay, so that's sort of the other thing. However, especially with modern computing power, and especially well, like in some of the bigger models that I've been involved with, a lot of times we run them on the high performance computing thing. So you set it and you come back a couple of days later when it's done. So that's not so much of an issue. So that is the sequential method, though, is that we're going to keep sampling until we hit our desired result. And okay, so how do we implement that? Well, if you remember what we did for a fixed sample size is we wrapped our execution. So this was our execution, reset and start simulation. That's reset initializes things. And then if we're using that inner stat resetter thing that we came up with the other day, we don't have to reset them in between because that reset will do that for us. So this is the execution of the simulation. And then we update our outer stats. So when we were doing that in a for loop, we did it for a fixed number of times. So this is kind of back to the programming thing. If I'm executing a particular task, a fixed known number of times, then a for loop is what you use. However, if I'm executing something where the number of times is unknown, or depending on some criterion, then a do loop or a do while loop is what's required. In this case, I want to make sure, and you can implement it either way. You can either do it as a do or a do while. For whatever reason, I tend to do them as do whiles, mostly to just make sure that it executes exactly once. If you remember, that's the difference. A do loop will only will execute 0 or more times. So if it executes 0 times, then that doesn't do it for me. A do while will execute at least once. So that's my reasoning. Okay, so what I'm going to do is I'm going to just sort of just increment the replications. The quantiles are going to be different, as before when we had a fixed, we had n like 30 replications, say, then we can get that quantile. But here we need to get the quantile of the particular replication, -1, of course. And then compute our half width for that. In this case, what I'm going to focus on is the delay in Q one. That's where this is from. And then now here's the criterion. So I've decided this is my beta, my desired half width. Here's the half width that I computed in this replication. That updated for that replication. And then now, okay, so now what's this about? Well, it turns out that sometimes what happens is if you only run it a couple times, then just by chance, you might get a really small half width just because of just running it a couple times. And you don't want to remember the in order for this formula to be valid, we need, we're saying that we need at least 30 observations. So this criterion ensures that we have at least 30. You see that? So otherwise, if we don't have that, and this actually happens sometimes, is just by chance we'll exit early with like only 5 replications, and that's not legitimate. So here we know we're going to have at least 30 of these things, so the half width we get we can be legitimate. Okay, so let's look at let's see what this looks like. Here. Okay, so this is so let's look at the terminating case. For the Java, I have it on for both the terminating and the steady state. So we'll do the terminating first. This is what we did yesterday with the fixed sample size. And if you remember, when we ran it, we saw, okay, here's our one of our measures. So the one that we're most interested in is the delay in the queue. Why that one? Just whatever. Okay, either that or the time in the system. Delay in the queue is something I usually like to focus on because the time in the system, I mean, a big piece of that is going to be our service time. So we don't have a lot. I mean, we do and we don't have control over that. Well, once we're in the simulation, we have control over that. Outside of the simulation in the system, that's something we can kind of, those are some of the levers we can pull. We can improve our server performance through training, through upgrading, through getting better machines, faster, whatever. The delay in queue is really, to me, kind of an important thing because when you're waiting online, does anybody who likes to wait online? Nobody. Why? Because that's completely, I mean, especially before the era of phones, smartphones, but where you can kind of check your email or something. But basically, it's like, why are you waiting online? Because there's something you want to have done. I mean, that server has. And when you're waiting online, they don't even know you exist. You're spending your time, and you're not getting any closer to your goal really because they're not working on you. I mean, if you're getting served and it's taking a little longer, I mean, that can be annoying, but at least they're working on you. Okay, so waiting in line is just total waste. So that's why I'm kind of interested in that. And then we did everything right. We got our 30 replications, and we have our confidence interval, and the half width is like 8.7, 8.57. And that's a lot. Okay, so so if you pull yours, you will see, and I think it's in the, okay, there's one called, I always have a problem with, they analyze entity server sequential. So this is implementing the sequential method. So let's see what that is about. So we have all the setup, the arrival process, the server, all of that is the same. And our inner stats, those are all the same. Okay, we're using our little inner stat resetter here to reset them. We're listening to them as a property change listener. Only now, okay, so now instead of a fixed sample size, I'm going to say my desired half width is 1. Okay, why 1? I mean, it could be anything, but I chose 1. Where does that come from? That comes from how tight I want my confidence interval to be. And this is how confident I want to be. Okay, so those are 2 slightly different things. And then, okay, so we have our outer stats, same thing. This is transient. I'm going to run it for the same. I'm going to run it for 10,000 time units. That's the transient one. Okay, so here's how I set that up. Now notice that I need, I'll need the quantile. And then and then the half width. And I'm defining those outside here because I need to, because that, and then I'm going to count the replications. Okay, so here I do the simulation, remembering that the inner stats are going to be resetted automatically. I update all my outer stats. That's something that we were always doing. And then now, okay, so I'm incrementing incrementing the replication. I could actually get that from the stats, but computing the quantile from the student T. And here I'm using the degrees of freedom from the replication because it's going to be different every time. Eventually this is going to converge to a normal, of course, but I don't, especially early on. The T distribution has much heavier tails than the normal distribution. So you want to, you don't want to be overconfident. So if I were to use the normal distribution instead of T, I would be creating confidence intervals that were smaller than they had any right to be. They were not true 95% confidence intervals. Okay, and then I compute my half width. So that's the standard deviation times the quantile divided by the square root of the count. And then, because, okay, so here's the thing, when you're running in a do or a do while loop, and that might be taking a little while, what you're doing is basically staring at a blinking cursor, and how do you know anything is going on? Okay, so what I'm going to do, or my way of doing this, is every 10th replication, I'm just going to say, oh, here I am, just to make sure it's working. Otherwise, you're sort of staring at it. This one doesn't take that long. The next one will, but okay, as you can see, we're kind of humming along. Now, notice that, see here at 30 you see notice that it kind of started like at about 4, then it kind of bumped up to 8, and now it's kind of gradually decreasing. And then, let's see, that took about 30 seconds. And then here's our confidence interval is plus or minus like 0.9. That's less than, typically it'll be less, just because it's rare to hit it exactly, of course, but, and then notice that the other ones, just that I was carrying along, also have reasonably tight ones as well. Okay. So, 31 seconds is not too bad. Before, when we were just doing it with the fixed sample size of 30, I think it like took 2 seconds or something. So, okay, so that's the transient. So you see how that goes? Now, what about steady state? The same principle applies for steady state, except we have to do the whole steady state thing again. So here we are. We're setting up the simulation itself here. And here, I have a same values as the other day. Truncation point of 30,000, I'm going to run it after that for 100,000 time units. And then just for the tally stats, I just chose a truncation quantity of 700. I could have been a little more precise with that to try to estimate roughly how many observations we would have at the truncation point. I didn't do that, but that would be a better way to carry on. But I'm using the truncating versions of all these, resetting those as well, and same confidence level of 0.05 and a desired half width of 1. Same as before, except in steady state. So I do everything now is exactly the same. And what's the only difference? The only difference is how I'm running the simulation. So I'm running it for this, or is it my stop time, is the truncation point plus the run length. And so when I run that, as you can see, it's a little bit slower. So as you can see, there isn't as much fluctuation in the values, and that's because we're running it for far longer. So in steady state, we're running for 100,000 time units, however many customers that is, and we're taking the average of that. So even though the averages are correlated, the variance of that of those averages is significantly less than for far fewer ones. But okay, now notice you can see in practical terms that 1 over root n convergence. You know that. Did they talk about big O convergence in any of your classes? Have you heard? No. Yes, no, a little bit. I mean, it's usually presented in very kind of abstract, ethereal things, but it has very significant real life consequences, and this is one of them. You know, the convergence on this is 1 over root n. That's very slow. You can see that it's really slow. So, in other words, if you look at the differential, as each of these are kind of 10 observations apart, and you see that overall they are decreasing. I mean, after a while, the estimate of the standard deviation is getting close to the real one, so that's not going to fluctuate so much. The t distribution is kind of, at this point, it's indistinguishable from a z. But we still have that 1 over root n. And as you can see, it's just kind of chugging and chugging and chugging, and we're like still 0.1 or so away. And it's still churning and churning. So I forget. Let's see. When I think I printed out. Yeah. Basically, I think it finally ended around. Okay, it should be ending soon. Almost there. There we go. Okay. So that took about 3 minutes. And we have a half width, which is less than 1. And then, just the other measures are correspondingly smaller. Okay. And this is what this approach is, something which is, I hope you can kind of see the value of it. Like now, I'm 95% confident that my true expected delay in Q in steady state is within 1, let's say minute, hour, of the actual one. And so I'm much more, I mean, I have the same confidence in this, but I have much greater accuracy. And you can only do this with a sequential method like this. Because again, if you fix the sample size, you're stuck with whatever confidence interval you have. Okay, that's that. And then just for now, as I mentioned, for the Python folk, there's yeah, I was having trouble with my implementation. I found, but if you remember, this is the fixed sample size for Python. Running it for 10,000 time units as I was in the Java one. And the numbers come up different, but this is a different implementation, but it's the principle still holds. And well, Python is quite a bit slower than Java, as it turns out. But that, in and of itself, that's not necessarily a reason not to use Python, but okay, so for this one, actually, for some reason the delays in queue were a bit tighter, but here's the same thing sequentially, and here, now, and Python doesn't have a do while; it just has a while. So, so I have to basically kind of turn things around. So I say while. Again, I need to keep the replications less than 30. That is, I keep doing it until I hit 30. And while the half width is bigger than the desired half width, then I want to keep doing it. And as before, I'm kind of printing out the half widths as we're going, and then we finally got to be less than 1. So that's for the transient case. So I have not implemented the steady state one in Python yet. So but that's coming. Okay, so that's the sequential method, and so you can do it fixed sample, you can do sequential if that's generally my preferred way if I have a choice. Okay, so now what's next? Well, there's actually a whole lot more we could talk about, but I'm not going to talk about it this time. There's actually, over in OR, they have a whole quarter-length course in just analyzing. They have one course like this where you learn how to create a simulation model, and another course where they spend the whole quarter analyzing. Why? Because there's something called experimental design, which is actually a very effective way of running simulations and doing a lot of what-if analysis. So, like for the system that I was analyzing today, we got a nice tight confidence interval on the delay in queue. The problem is that tight confidence interval and that estimate is too big. It was like 30 something. And so the next, the next thing is, okay, how can we improve that? And that involves things that are kind of outside of the specific realm of, of the simulation. But with some of these what if types of things, you could ask something like, well, what if we added a server? And since I actually have the time, let me, like, what would this do? And let me do it on the, where are we here? We had 2 servers. So it's like, I don't like the delay in queue. What can we do? We can speed up the servers, so I could try to decrease the service times, or I could just, what would happen if we hired another server? What would happen then? And then, well, and as you can see, hiring another server, all of a sudden, our delay in queue is like really, really small. And then the question comes up is, okay, is what we saved in terms of people not being pissed off for having to wait so long, was that worth it to sort of hire another server or buy another machine or whatever that is? And that's outside the scope of this analysis. But with this analysis, you could at least ask that question and have it answered. Okay, so that concludes the material for this course. As I said, there's going to be one more assignment. I was hoping to have it yesterday. I'm almost there. It'll be very, very shortly. I'll have it posted. Given the fact that the final is next Tuesday, I have kind of a short, I'm gonna have it due Friday if that's, yeah, I hope that's not too much of a hardship. It's gonna involve this, the same entity server that I've been doing here. And the only thing that you're gonna be doing is implementing the Pareto distribution and the Rayleigh distribution that I asked you to do in the written assignment. So implementing those and then using those in this model to come up with some analysis. That's what it involves. So it's fairly straightforward, but implementing those random variates can be a little tricky, but straightforward. There's and there is an example. Let's see, let me verify this. There should be an example. Yeah, or several. So, you know, actually, 1, 2. Yeah, there are 3 examples in the random, the MV302 random package in your class code. So kind of use those as kind of a model for how to do yours. Okay. Any questions, concerns? So, and again, tomorrow I'll be on Zoom for the 11 o'clock and the 1 o'clock times. So any questions, you can kind of come on. If there are no questions, then you can use the time to work on the assignment. Yeah. Yes, yeah, there'll be a solution for that. Yeah, no, I'll have a topics list as well. Yeah, just for those listening, if you didn't hear, the question is there going to be a solution for the sample final? And the answer is yes. And is there going to be a topics list as for the midterm? And the answer is also yes. And then for those online, again, the final will be the same protocol as for the midterm. You know, you'll log on to Sakai, download the thing, and then upload your solutions.